Hello, this is the next video in a playlist that I'm calling Introduction to Mathematical Statistics. We're in Chapter 2, part of this playlist that I'm calling Discrete Random Variables. And let's jump to today's topic, which is the Bernoulli distribution. Now, a Bernoulli random variable has two possible outcomes, such as head or tail, success or failure, defective or non-defective. The possible outcomes of Bernoulli random variable will be denoted by 0 or 1. Generically, and we may be interested in defectives or non-defectives, but we're going to model it as 0 or 1. A random variable has a Bernoulli distribution with parameter p if x can only take on the value 0 or 1, with p equal the probability that x is a 1, and 1 minus p, or often called q, is the probability that x equals 0. The density function can be written as follows. And yes, density function. It's a density function of discrete type. Some would call it a probability mass function. Both are fine. So f of x given p is p to the x, 1 minus p raised to the 1 minus x. X takes on the values 0 and 1. Now note f of 1, so we plug in 1 here and we get p, which is the probability that x is equal to 1. F of 0, we plug in 0, we get 1 minus p, which is the probability that x is equal to 0. Let's let x be a Bernoulli random variable with parameter p. The mean of x is given by p. And let's prove that. So the expected value of x says take x times its density, summed over all possible values that it can assume, which are just 0 and 1. So you plug in 0, you plug in 1 everywhere. 0 times anything, 0. 1 times f of 1, and f of 1 we said was p, and we're done. Let x be a Bernoulli random variable, theorem 18 in chapter 2. Let x be a Bernoulli random variable with parameter p. The second moment of x is given by p. And the more you do this kind of stuff, you instantly know that it's p, because since x is a 0, 1 random variable, when you square each of those values, you get it back. So x squared and x are the same in a 0, 1 random variable, a Bernoulli random variable. So proof is this: probability that x, the expected value of x squared, you take x squared times its density summed over all possible values. You plug in 0 everywhere, add it to plug in 1 everywhere, you get p back. Let x be a Bernoulli random variable with parameter p. The variance x is given by p times 1 minus p. You'll often see this as written as pq, because it's easier to write q than it is to parentheses 1 minus p. So the proof is this: the variance of x is equal to the expected value of x squared minus the mean quantity squared. So you plug in the values that we obtained earlier, you factor out a p, and you get p times 1 minus p. That's what we wanted to show. Let x be a Bernoulli random variable with parameter p. The moment generating function of x is given by this equation here: p times e to the t plus 1 minus p. Some will put a q there. Let's prove it. So the moment generating function of x is the expected value of e to the tx. And so that says take e to the tx times its density summed over all possible values. So you plug in 0 everywhere, plus you plug in 1 everywhere. E to the t0 is just 1. F of 0 is 1 minus p. E to the t1 is e to the t. F of 1 is p. Well, that's what we wanted to show. Now, some nomenclature that we're going to use in upcoming videos. It's the concept of Bernoulli trials. And we're going to use it over and over and over. And so I wanted to define it. Let xi, I goes from 1 to n, be a sequence of independent Bernoulli random variables with parameter p. Now note, n can be infinity. The sequence xi forms a sequence of Bernoulli trials with parameter p. So in our next video, when we look at what's called the binomial distribution, we'll assume we'll say stuff like, assume we have a sequence of Bernoulli trials, of size n, or something like that. And then you can also say an infinite sequence of Bernoulli trials with parameter p. Anyway, I just wanted to introduce that, and I think we're done with this video. So hopefully you enjoyed this. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.